Hello again. We are continuing our discussion of limits, and now we're moving from talking about limits of sequences to talking about a familiar subject, the limit of a function. And we did talk about this in Unit 1, but it doesn't hurt to talk about it again since that was quite a while ago. Let's review some of the strategies from that video. The first strategy was if you can substitute the x value into the function directly, then you're going to do that. And I've given you a couple of examples there. You're just going to plug that x right into the expression that you're given. If that doesn't work, if you get 0 over 0 when you do that, then another strategy you can use is you can try to factor the numerator and the denominator completely and see if any of those factors divide out. Okay? And then another strategy, when I have fractions within fractions, then what I can do is I can find a common denominator either with the fractions in the numerator or with any fractions in the denominator. And hopefully when I do that, things will simplify to a situation where I can plug in that original x and come up with a number that's not 0 over 0. All right, and then if I have square roots, and you've seen this before, I can multiply top and bottom by the conjugate of that expression that has all those square roots in it. So if you look at that numerator, that's root x plus 5 minus root 5. So since that's the one that's causing the problem, I can multiply top and bottom by the conjugate of that expression, and then things should simplify out nicely, hopefully. All right, and then if I have parentheses, I can always expand those out, see if things will subtract or divide to simplify and give me something that's nicer that I can plug that original x into. All right, so how can we tell if the limit actually exists or doesn't exist? Well, we have two limits that we need to consider. There's the left-hand limit, which uses x's that are a little bit less than the x that I'm looking at. And there's a notation for that with a little minus after the value that I'm getting close to, x is getting close to. Okay, and then the right-hand limit is very, very similar, but it's got a plus instead of a minus, so that means I'm looking at x's that are a little bit bigger than the x that I'm trying to find the limit at. All right, so if the left-hand limit and the right-hand limit exist but are not equal to each other, then the limit doesn't exist. Okay, so here's an example. As you see, the left-hand side of the function before that break approaches a certain y value. The right-hand side of that function approaches a different y value. So what you'll notice is the limit doesn't exist at that point. It probably exists everywhere else, but just not at that point. Okay, so some more examples of where the left-hand side and the right-hand side are approaching different y values, which means that the limit at that point doesn't exist. All right, so here's an example. I have a piecewise function here, and I want to know if the limit exists at x equals 2. Okay, so I need to make sure that the left-hand limit and the right-hand limits are equal. So looking at the left-hand limit, as x approaches 2 from the left, I'm looking at x's that are a little bit less than 2, which means I need to plug 2 into the first piece, just to kind of see what the y values will approach as x approaches 2 from the left. So if I plug in 2, I'm going to get a y value of 7. All right, and then if I look at the right-hand limit, now I'm looking at x's that are a little bit bigger than 2, so I need to plug in 2 into the right side, or the second piece of that function. And if I do that, I also get 7. Okay, and so what I notice is as I approach 2 from the left, f of x approaches 7. As I approach 2 from the right, f of x approaches 7. Since they're approaching the same value, then the limit does exist at x equals 2, and it has a y value of 7. Another example, same situation. I've got a function, x is approaching 4, and I want to know if the limit exists. So I'm going to look at the left-hand limit and the right-hand limit again and see if they are approaching the same y value. The left-hand limit, what you'll notice is I've got that absolute value in the denominator, and all you need to do is take some x's that are a little bit less than 4 and plug them in for x into that denominator, and what you'll notice is that x minus 4 is negative. So if I want to take the absolute value of a negative, that means I need to change the sign of it. So in those cases only, the absolute value of x minus 4 is going to be negative x minus 4, meaning I change the sign of it to make it positive. So I can make that replacement in my function, and what I notice is the x minus 4's on the top and bottom divide out, and that leaves me with x plus 4 over negative 1. If I plug 4 into that, then I get negative 8. So now let's look at the right-hand limit. As x approaches 4 from the right, go back to the original function and try plugging in x's that are a little bit bigger than 4, and what you'll notice is that absolute value of x minus 4, the x minus 4 is going to be positive, so you don't need to change the sign at all, and it will behave just like x minus 4 for those x's that are a little bit bigger than 4. All right, so when I replace absolute value x minus 4 with just x minus 4, that's the function I get. And again, the x minus 4's divide out, and that leaves me with x plus 4 over positive 1 this time, which I don't need to write the positive 1. If I replace x with 4 in this new function, then I get a y value of 8. So as x approaches 4 from the left, I get y values of negative 8. As x approaches 4 from the right, I get y values of 8. These are not the same number, so that means that the limit does not exist. So there's an example of each kind where the limit does exist and where the limit doesn't exist. If you have any questions about that, please let me know, and I will see you tomorrow.